So for theory, shear stress is the force applied on per unit area of the member, whereas the shear force is the resulting force acting on any one of the parts of the beam normal to the axis. Shearing forces are linear forces pushing one part of a body in one specific direction and another part of the body in the opposite direction. When the forces are aligned into each other, they are called compression force. An example is a deck of cards being pushed one way at the top and the other at the bottom, causing the cards to slide. Another example is when wind blows at the side of a big roof of a home. The side walls experience a force at their top pushing in the direction of the wind and their bottom in the opposite direction from the ground or foundation. William A. Nash defines shear force in terms of planes. If a plane is passed through a body, a force acting along this plane is called a shear force, a shearing force.
Hi, as you know, my name is Samsul. My message number is DN214030. I'm from Group 2. So I will explain about my experiment for shear force. So for the first, we will explain about objective, which is measure the stress distribution, bending force and strains across the section of a beam. So number 2 is to understand the relationship between stresses and strains within a structure in a relation to bending roots. And the third is to understand the relationship between a bending moment and the stress at the various positions. So for the equipment list, we're going to use a ruler and then a beam, also rolling pivot. This is pivot tool, and then a thumb screw, this one and this one, and then we're going to use a digital force display, hand mesh, also mesh. So we're going to explain about experiment setup. So for the first, make sure the digital force display is on, and then carefully set the 0 for the first meter using the gear left hand beam of the experiment. So set the 0 for the force, and then gently apply the small load with the finger with the center beam and the radius, and then must put the mesh in the hand.
My matrix number is CN200-224. So for now, I would like to explain about the experimental procedures we carry out throughout our experiment. So as all the safety measures had been done perfectly, so we are going to continue with our experiment 2, which is shear force variation for various loading conditions. So before we start our experiment, we have to make sure that our digital force display is set to 0. That's the important thing. So let me see the figure 3.6 shows that there are one load which weighs around 400 grams and should be placed right left to the rolling pivot with the length of 140 mm. So before we place our load right to the left, we have to make sure that the length is 140 mm from the left rolling pivot. So this is the point where we have to hang the load, which weighs around 400 grams. And also we have to make sure that this thing is not moving up. I mean the hook. Okay, for now for figure 3.7, it shows that there are two loads which carries, this one is 400 gram and this one is 200 gram. So let's see the 200 gram. So the 200 gram load has to be placed right right of rolling pivot with the length of 220 mm. Let me check the length first. Let me measure the length first. 220 mm. So it shows right here. Okay, the second load, 400 gram, should be moving right from the rolling pivot with the length of 260 mm. So we have to have the second load right here. Make sure the masses are not moving. It has to be so stable so that we can get the value precisely. So all the loads are being set up perfectly. Let's see the digital force display. Shows that 1.4 Newton for this figure 3.7 experiment with two loads. Thank you. So carrying to the figure 3.8. So there are two load also. This load carries around 500 gram. This one is 400 gram. So for 500 gram, it should be placed right to the rolling pivot with a length of 240 mm. So this is where we have to place the 500 gram load. Okay, the second load is 400 gram, where it should be placed 400 meter from left from the rolling pivot. So this is where we have to place the 400 gram load. So all the loads are placed perfectly. So let's see the digital unit reading in the digital force display. So it shows that 2.2 Newton for figure 3.8 diagram carrying two loads, which is 500 gram and 400 gram. So that's all from me. Thank you. So for now, I would like to explain about the result and data we have gained from the experiment shear force. So for the mass 0 gram, the experimental shear force will be 0.1 and the theoretical shear force is also 0. So for 100 gram with the load of 981, the experimental shear force is 0.7 and the theoretical shear force is 0.579. For 200 gram with the load of 1962, the experimental shear force is 1.2 Newton and the theoretical shear force is 1.158 Newton. For 300 gram, the load for 300 gram with 2943 got the experimental shear force is 1.7 and the theoretical shear force is 1.737. So the 400 gram, the load 3924, the experimental shear force is 2.2 and the theoretical shear force will be 2.316. For the last one, with the mass of 500 gram and with the load of 4905, the experimental shear force will be 2.7 Newton and the theoretical shear force will be 2.895 Newton. So for experiment 2, for figure 6, we got the work one for 3.92 and the W2 for 0. And experimental shear force will be negative 1.2, where RA stands for 5.167 and RB stands for negative 1.247, and the theoretical shear force will be negative 1.247. For figure 6, W1 is 1.96 and W2 stands for 3.92. Experimental shear force will be 3.0 and RA stands for 2.584 and RB for 3.296. So for the theoretical shear force, it will be 3.296. So for the last one, figure 8, W1 will be 4.91 and W2 will be 3.92. The experimental shear force will be 2.4, where the RA stands for 6.242 and RB for 2.588. The theoretical shear force will be 2.322. So for the graph of experimental shear force versus theoretical shear force, we are going to look at the coordinates first. The y-axis stands for experimental shear force in Newton and the x-axis stands for theoretical shear force. So the first point stands for negative 1.247 for x-axis, and for the y-axis is negative 1.2. For the second point, the coordinate for x-axis is 2.322 and for y-axis is 2.4. And the last coordinate for the last point is for x-axis is 3.296 and the y-axis is 3.0. So to find the gradient, we have to just insert the values in the formula, which is y2 minus y1 over x2 minus x1. So we'll get the answer. The answer is 1.0087. So for the observation, for the first experiment, two graphs were plotted to show the relationship between the experimental shear force versus mass. The trend graph for both graphs shows the relationship between the shear force against the mass are directly proportional, which means as the mass increases, the shear force also increases.
So our conclusion, our group managed to examine how shear force varies with an increasing point load. Our group also managed to examine how shear force varies at the cut position of the beam for various loading conditions. This experiment was subjected to study the effect of a different force magnitude on shear force produced in the beam due to the force. Theoretical calculation of shear force show that there is a direct relation between load and shear force, but the experimental shear force shows some errors which can be due to the personal error of faulty apparatus. This experiment is a success of our group and fulfilled and its objective. So that's all from us. Thank you.